on section 7.8, which is a section that talks about repeated eigenvalues. For matrix equations. So, okay, so we know we're studying matrix equations in the form x prime equals ax. And we're looking for the general solution if we have an initial condition. If you know something like x at t0 is equal to a fixed vector, x, let me call it super zero, okay? Then we find an exact solution, an explicit solution. If it's just this equation, you can find the general solution. And we've seen the case where we already did. One, when you have the eigenvalues of A are real and distinct. Or repeated with multiplicity m, and we can find m linearly independent eigenvectors. Okay, so that was one case that we studied. That was the first case that we studied. Earlier today, I lectured on 7.6, where we had complex eigenvalues. And they always occur in complex conjugate pairs. Because we start with real matrices. So if you have complex eigenvalues, they always occur in complex conjugate pairs. But even in 7.6, we only looked at simple eigenvalues, that is, eigenvalues of multiplicity 1. Because if you have repeated multiplicity, if you can find, they can have multiplicity m as long as you can find m linearly independent eigenvectors. Here, we look at eigenvalues of multiplicity m, but we can find only m minus 1 or fewer linearly independent eigenvectors. And then the situation becomes a lot more complicated, as we'll quickly see. All right, so I'm going to do this first in the context of an example, because to just try to say what you can do in general is really confusing. So let's try to do it in an example, and I'll explain how you handle it step by step. And then it's easier to apply it in different cases. So let's look at the matrix equation. X prime equals 1, 1, 9 minus 5. Sorry, 1 minus 1, 9 minus 5 times x. And let's say our initial condition, x sub 0, is 1 minus 1. Okay. All right, so we need to, and you want to find the solution. Now, because we have a set of initial conditions, we can find the exact solution, the explicit solution, okay? No arbitrary constants. All right, so step 1, as always, find the eigenvalues of A. Okay, so we look at the determinant of A minus lambda I and set that equal to 0. So that's the determinant of 1 minus lambda, 9 minus 1, 5 minus lambda. So that says 0 is equal to 1 minus lambda times 5 minus lambda plus 9. Okay, so that is going to be lambda squared. You have a minus 5 lambda and a minus 1 lambda. That's a minus 6 lambda. And then you have a plus 5 and a plus 9 is plus 14. So that's plus 5 and plus 9, that's plus 14. Okay. All right, and 14 is, now let's see, hold on, let's see, let me make sure we didn't, that I copied this right. Sorry, this is a -5 minus lambda. No wonder something looks amiss. There's a -5 there. So this gives me a +5 lambda and a -1 lambda. So that gives me a +4 lambda. And then I have a -5 and a +9. So that's +4. Okay, now we're going. This is the example I want. So this is lambda +2 quantity squared when you factor it. So lambda equals -2 is an eigenvalue of multiplicity 2 because this is a square. Okay. All right, so we try to find an eigenvector. Okay, so we hopefully can find 2 of them, but we know there's at least one, but we're really hoping for 2 because this is of multiplicity 2. All right, so let's see. I have to look at a minus a -2, so that's +2 times I. Let me call it x sub 2 is the eigenvector for that. It has to be equal to 0. In other words, a plus 2I is you add 2 along the main diagonal, so this will be 3 minus 3, 9 minus 1. Okay, that's a 9. Let me call the vector components x, y, and that equals 0, 0. Okay. All right, so that says 3x plus 9y equals 0. And then you notice that this is going to give me the same thing because this says minus x minus 3y equals 0. And these two equations are the same because if I multiply the bottom one by -3, you get the same exact equation. Okay. All right, so that means they're the same equation. That means you only need one of them to give you the information. And so both of them say that x is equal to -3y. Okay. So an eigenvector for 2, or for -2 rather, is something of the form, if I pick y to be 1, then x is -3. Okay. All right. So that's an eigenvector. But you notice there's no other constraint. There's no way to get a second linearly independent eigenvector. Because the general solution for that, because it's a second order, it's a 2 by 2 matrix, I need 2 linearly independent solutions. So I'm going to need to find a second linearly independent eigenvector. Okay, and so now that's where things get a little complicated. You remember that when you found when we built our solution, if this was the eigenvector, one term in the solution would look like e to the -2t times the eigenvector. Okay, so this is one term in the general solution. Looks like this. So remembering back to what we did with repeated roots when we had just equations and not matrix equations, we would guess, so for equations, not matrix equations, for the second linearly independent solution, we normally would guess t e to the -2t, okay? Okay. So if we try t e to the -2t times our eigenvector and see if that works, does this work? does this give a second linearly independent solution? Linearly independent eigenvector? And the answer is no, it doesn't, okay? It doesn't. So you have to do something more complicated. What you have to do is you guess and so this is just a general rule. This is how you guess. You guess what you hoped would work. Okay. Plus, you take another vector, we call it eta 1, eta 2, times e to the minus 2t, times your e to the eigenvalue, okay? So in other words, we're guessing t e to the minus 2t times c, where c is a vector, the eigenvector. This is the eigenvector for lambda equals minus 2 plus eta, okay? And this is where eta satisfies that a plus 2 times I times eta equals c, okay? And that might seem really confusing, and it is a bit, but notice that if I applied the operator a plus 2i again to both sides, this is a matrix, let me call it a matrix. On the left, I would get a plus 2i squared times eta, and this would be a plus 2i times c. But since c is an eigenvector for the eigenvalue minus 2, this is equal to 0. So notice what this does. Eta is a vector so that when I look at a plus 2i to the second power of times eta, that gives me the 0 vector. Okay, so it's sort of like you take the same power that is the multiplicity. That's what you want to have to work out. And right now we're doing it just for multiplicity 2. That's bad enough. Okay, so bottom line is, if you do the obvious guess, that will not work. So what you have to do is you take your original eigenvector, and I don't think, yeah, maybe I do. Here's a pen with a different color ink. Here's my original eigenvector, and I multiply it by t. That's part 1 of my guess at my second linearly independent solution. And then I take an arbitrary vector, eta, well, it's not really arbitrary, times e to the minus lambda t. Lambda is minus 2 for us. And eta has to satisfy that a plus the a minus the eigenvalue times the identity applied to eta gives you the vector, the eigenvector you started with. Okay, so now so we have to find an eta that satisfies this. So let's look at what that says. Okay, so let me do this on a different sheet. So eta plus 2i, I said it wrong. A plus 2 times I. So that is adding 2 along the main diagonal. So that's 3, 9, minus 1, minus 3. Okay. And then I have to take that times a vector eta, which I said has components eta 1, eta 2. And that has to be equal to the 2 components of my eigenvector c, which was 3 minus 1. So this is my vector c. the eigenvector that corresponded to lambda equals -2. Okay, and now that gives me two equations and two unknowns. It says 3 eta 1 plus 9 eta 2 equals 3. And it says minus eta 1 minus 3 eta 2 equals -1. Okay, and notice those are the same equations, because if I multiply the bottom one times 3 or -3, I get the exact same equation as the above. So these are the same equations. So I only need to use one because the other one isn't going to give me any extra information. So from this equation, solving for eta 1, it says eta 1 is going to be minus 3 eta 2 plus 1. So in other words, if I pick eta 2 to be anything, your favorite number, pick eta 2 to be, I don't know, let's say k, any k not equal to 0, okay? Then eta 1 is minus 3k plus 1, okay? All right, and so that says that my vector eta, then big vector eta, looks like k 1 minus 3k, okay? All right, and so now the second linearly independent solution to x prime, to my original problem, x prime equals ax, is, we call it x2 t. So this will be t e to the minus 2t times 3 minus 1. This is the one I had, my original first solution, and I multiply it by t. Sorry, I smeared that by putting my finger on it a little too quickly. And now I take plus 1 minus 3k, comma k, times e to the t for any k, okay? And notice that this could be written as t e to the minus 2t, 3 minus 1. And you could write this as, let me do it this way, minus 3 minus 1 plus 1 comma 0. This should be times k, e to the t. This should be e to the minus 2t. Okay. And so basically this is, now when you look at this term, this one with the e to the minus 2t, that's a multiple of this guy. Is a multiple of our first solution. So we don't need to include that part. Because it doesn't give us anything extra into the general solution that x1 didn't already. So all we need out of x2 then is the t e to the minus 2t times 3 minus 1. And then you have minus 1, 0. And this is any k, so you could just as well write it as plus if you wanted to, because you could take k to be minus 1, e to the minus 2t. All right, and so then finally, a general solution, x of t is c1 x1, which is the first solution we found, plus c2 x2, which is this solution we just found. And so c1 x1 was e to the minus 2t, 3 minus 1. And then we get plus c2 t e to the minus 2t times 3 minus 1 plus c2, I'll just write it as c2 comma 0 e to the minus 2t. Okay. All right. Now, technically, we have to go back and finish we have to figure out the initial conditions using C1 and C2 using the initial conditions. So remember, us initial conditions were that 1 minus 1. All right. So x of 0 is 1 minus 1. On the other hand, x at 0, let's evaluate this thing. When t equals 0, this first one is C1 times 3 minus 1. And at t equals 0, notice this one goes away when t equals 0. And when t equals 0 here, I get plus C2 comma 0. Not comma, oh, C2 0. So this says 3C1 plus C2. And the bottom row says minus C1. And that has to be equal to this. So that tells me that minus 1 is minus C1. So C1 is 1. And the top row says that 1 is 3C1 plus C2, but C1 is 1, which is 3 plus C2. So that says C2 is minus 2. Okay, so now you can write down the final solution. So x of t is e to the minus 2t times 3 minus 1. And C2 is minus 2, so this becomes minus 2e to the minus 2t times 3 minus 1. Minus, well, how do you want to do it? You could do this, minus 2 comma 0 e to the minus 2t. Okay. Okay, so not easy problems, and it's a long process. The good news is because it's essentially an open book test, you can look up, you can look up the rule, like, for example, how you need, what eta has to satisfy. So you don't have to memorize it and get it all straight in your mind. Still, it's a long calculation and it's rather tricky.